All right, here we go. How can you sketch the graph of the inverse of a function? That is a great question. We've talked about this a little bit when we talked about inverses. What's the relationship? We switch the x and y values. So if I look at this, here we want to use the graph of f to sketch the graph of f inverse, which is the inverse function of f, on the same coordinate axis. So let's look at this and we'll do one of these together. So I'm going to pick some points that it looks like I can kind of see where they are, and then I'll talk about this. So if I look on y equals f of x, right? So that's the red line here. What are the xy coordinates right here at that green dot that I drew? Well, they are 4, 4. So if I switch those xy coordinates, that's the same thing. So if I say the green is f, and I'm going to say blue is f inverse, there's also going to be a point on the inverse right here. If I look at, let's say, this point right here. So that looks to me like it's maybe at approximately 5, 6. So then on the inverse, there's going to be a point that is approximately 6, 5. So I plot that. Let's pick another point, and so let's go right here. So that looks like it's maybe at 0, I don't know, it's a little bit more than -2, but for the sake of example, I'm going to say -2, so then I know that at -2, 0, I would have a point. Now, again, I know this point here was a little bit more than -2. It's maybe like -2.5, so that's where I'm actually going to put the point for the inverse. And then let's pick one more. So let's look at this point here, and that looks as if it's at -2, -6. And so then I know on the inverse, there should be -6, -2. So -6, -2. And now I'm going to connect these. And that should be what the inverse looks like, relatively, right? It's not perfect, but it gives me a general idea. So literally what I'm doing is I'm finding points, I'm switching the x and y values, and then I'm just connecting those. Now, I knew that there wasn't going to be any sort of funky curve on the inverse because the original function is a line. So the inverse should also be a line. All right, I want you to try and do B. So pause the video, do B, unpause when you're ready to discuss. Okay, so again, this isn't perfect, but I was approximating this point is kind of like 1, 3. Not exactly, but then I'm going to have a point 3, 1. So I plotted that right here. And this point here is like 4, 5. So I'm going to have a point 5, 4. This point here looks like it's kind of like 9, 6. So then I'm going to have a point 6, 9, which I plotted right here. And then I draw that curve to make the shape, and boom, that's my inverse. Nice work. Let's do 2 more, just for fun. We've got this. So I want you to do C and D, both of them. Pause the video, unpause when you are ready to discuss. Okay, so for C, here are a bunch of points that I plotted for, or that I identified from the original function, -4, -6, -3, -2, -2, 1, 0, 2, 2, 3, 3, 6. So then I switched all those x and y values and I plotted those points, and that's how I got the blue. For D, it was a little bit easier just because of the shape. So here, I didn't write these down, but this is the point 0, 2, so I plotted the point 2, 0. This point here, I called 2, 5, so I plotted the point 5, 2. And then I had a point at 3, 8, so I plotted the point 8, 3. And then on this side, it looks like everything kind of planes out at +1. So I just this was -4, 1, so I plotted 1, -4, and then kind of showed that general shape. Okay, so those are my inverse graphs. Now let's talk about one other thing here, or 2 other things actually. So notice this other line, this dashed line that has been here on all of these, and I labeled it, it's y equals x. Why did I label that? Why did I draw that? Great question, glad you asked. Glad you noticed. So I did that because if a function and its inverse are graphed on the same coordinate plane, then they should mirror each other or reflect or have symmetry about the line y equals x. And notice that it's kind of cool to see with this one because of what the shape of the graphs. But if I was to take the red graph and fold it over the line y equals x, I would get the blue graph. And the reason why that happens with inverses is because of what we said. We literally are switching the x and y values, right? So also notice that any of the graphs, so A, B, and C, if they cross the line y equals x, the inverse will cross at that same point, right? That will be an intersection point between the function and its inverse, is on the line y equals x, because there, when we switch the x and y values, it's still the same value. So that should make sense. So we see that intersection here. We see that was one of our points here. And then I didn't label it, but that was here as well. And then for D, the original function never crossed the line y equals x, so the inverse will never cross as well. All right, next one. So if we want to verify or determine if functions are inverses, one thing we could do is we could make a table of values. This is really convenient to do on our calculator. Okay, so if I do this on the calculator, though, I really have to make sure I understand what I'm doing and the relationship between a function and its inverse. So I put the function as y1, and I put the other function, which is hopefully the inverse, as y2. One quick note, when we're putting in x plus 1 over 3, make sure to put the x plus 1 in parentheses in your calculator here. Otherwise, it might mess it up for you. Okay, so if I look at the table, remember the relationship between x and y1 is the function. So on the function, there is a point -4, -13. There's a point -3, -10. There's a point -2, -7. And there's a point -1, -4. So let's focus on this point right here. So this is the x coordinate, this is the y coordinate. That means on the inverse, I should have a y coordinate of -1 when I have an x coordinate of -4. And I do. On the original function, I have a coordinate of 0, -1. So then on the inverse, I should have a coordinate of -1, 0. And I do. On the function, I have a coordinate of 1, 2. So then on the inverse, I should have a coordinate of 2, 1. See how that works? So that's how we can use a table. Now, what I was saying was we have to be careful and we have to understand that we're looking for pairs and then the switching of those, right? So for instance, if I look at this coordinate point right here, -4, -13. Well, I need to scroll to an x coordinate of -13 to make sure that the y2, or the other function, had a value of -4, right? And I see that worked. But that's just where I have to make sure I'm understanding what I'm actually looking at, because it's not saying that for one row on the table that things are going to work out. That's not how it works. And that should make sense, right? We're switching the x and y values, so they're not always going to match up that way. So making my table of values would look something like this, right? So these were some of the values from the original function, -2, -7, -1, -4, 0, -1, 1, 2, 2, 5. And so then these were values on the inverse, and I can see that those match up. So that verifies. Doesn't prove, but it helps me confirm, yeah, they're probably inverses. All right, last two. I want you to determine whether these pairs of functions are inverses of each other. There are many ways in which you could do this, all of which could be correct. So I'll leave it up to you to decide how you want to do it. Pause the video though, do that, and unpause when you're ready to discuss. All right, so for the first one, and I did this technique for both of them, and again, there's other ways we could determine this, which would be mainly graphical or using tables. But for the first one, I actually just figured, well, let's just find the inverse of f and see if it's the same as g, right? So I switched the x and y, so I said x equals y plus 5, I subtracted the 5, so I get x minus 5 equals y, so then f inverse of x is x minus 5. Wait a minute, that's also g of x. So yes, these are inverses of each other, because g of x equals the inverse of f. That's why, if you didn't. Anyway, so I did this for 11 as well. So f of x equals 8x to the third, g of x equals the cube root of 2x. So let's just go ahead and find the inverse of f. So I switch the x and y. X equals 8y to the third. Divide both sides by 8. Great. Now I have x over 8 equals y cubed in green. How do I get rid of a cube? I do the cube root. And we have learned that if I have the cube or any root of a fraction, I can do the root of the numerator and denominator separately. Conveniently, the cube root of 8 is 2, so that's why there's no more root in the denominator, and there's only a cube root of x in the numerator. So the cube root of x over 2 equals y, therefore f inverse of x equals the cube root of x over 2. Is that the same as g of x? No. No, it is not. So those are not inverses of each other. Again, other ways we could have done this, I could have graphed f of x and g of x on my calculator or on Desmos and looked and see, do they reflect over the line y equals x? Do all the x and y values switch? Look at the tables like we did on the previous problem. All of those would have been ways to help me determine if they're inverses as well. Okay, so again, we want to make sure we just understand the relationship between a function and its inverse, and that is literally switching all of the x and y values. Graphically, that's how we do this. Also, a few other things that we noticed in the graphs, that they reflect over the line y equals x, that they will intersect on the line y equals x if they intersect that line. Nice work.